this video, I want to talk about something that's given the grand name of the fundamental theorem for line integrals. Now, we've only encountered a very few fundamental theorems over the course of our lives. We have the fundamental theorem of algebra, which talks about how you can completely factor and break down a polynomial over the real and complex numbers. We have the fundamental theorems of calculus, which tell us about the relationship between the derivative and the integral. And today we have the fundamental theorem for line integrals, which is equally impressive, I would say, as the previous two. By the end of the day, here's what we want to be able to do. We want to define the terms conservative vector field and potential function. We want to state this fundamental theorem, and then we want to use some qualities which are called path independence, and we want to be able to use partial derivatives to show that a vector field must not be conservative. Okay, so suppose we have a parametrization of a curve C, and let's suppose that R of t is this parameterization. We say that the curve C is a closed curve if R of A is the same location as R of B. So in other words, the curve starts and ends at the same point. So to give you an example, this curve starts and ends at two different locations. This is not closed. But something like a circle, for example, or any loop that really concludes, this would be something that is closed, because the starting point and the end point coincide, bringing that loop, that curve, back together. Okay, now let's set that definition aside just for a second, and let's let F be a vector field. We say that the vector field F is path independent if the integral over C, the line integral over C of the vector field is equal to 0 for any closed curve C. Or if you want to think about this another way, the integral of vector field F over the curve C has the same value for all curves C having the same start and end. That means that if you take the line integral of F over this curve in blue here, you're going to get exactly the same result as if you take the line integral over this pink curve, the same as if you take the line integral over this cyan curve, the same as if you just moved in a straight line. The integral of F over all these curves being the same would mean that F gets to be called path independent. And that turns out to be logically the same thing as saying that the line integral over any curve that starts and stops at the same point, the result of that is 0. And that's just because, any curve that starts and ends at the same point would have the same ends as a curve that just stayed in that point and didn't move anywhere. And a line integral over a stationary point is equal to 0. Alright, now let's set that aside and let's introduce one more piece of terminology. A vector field F is called conservative if F is equal to the gradient vector of some other function. T bar function. So in other words, our vector field, the output of our vector field, P of xy, and q of xy is the same as what we get by taking f sub x at xy and f sub y at xy. So the vector field is the gradient of somebody else. And in the case that the vector field f is the gradient of the function lowercase f, then the function lowercase f is called a potential function. A potential function for the vector field f, capital F. Now, as an application of this third definition, one such application would be gravity, once again. The gravitational force field of an object is an example of a conservative vector field. It's the gradient of some other quantity. And the quantity whose gradient gives you gravitation is related to the function that gives you the object's potential energy, gravitational potential energy, which is where this term potential function gets its name, because the quintessential potential function is the potential energy function. Gravitational potential energy is related to the gravitational force field the same way that the potential function is related to this generic vector field. And we'll have an exercise in today's concept check that goes into a little bit more detail about the gravitational force field and the potential energy function. All right, so now we get to the fundamental theorem, where we get to put together all the ideas and definitions that we just ran through. So suppose that f is a conservative vector field. So suppose that f is somebody else's gradient. F is the gradient of somebody else. If that happens to be the case, then you are in incredible luck. If f is conservative, the first thing that you know is f is path independent. But not only that, if you want to calculate the line integral over a curve C, over the vector field R, then all you have to do is take a difference. Take a difference of the output of the potential function at the last point on the curve and subtract the output of the potential function at the first point of the curve. So it gives you the ability, if you can find the potential function for your vector field, it gives you the ability to calculate line integrals without doing any dot products, without doing anything with the velocity vector of the parameterization. We get to skip all that work, and all we have to do is plug these 2 points into the potential function and subtract them. It really is amazing. So let's do an exercise to really see that in action. Someone comes to me and they say, hey, for reasons that I am not going to make clear to you right now, the vector field f of xy, given in formula right here, this I know is a conservative vector field. So the first thing that I want you to do is to find the potential function that goes with this vector field. And then I want you to calculate this particular line integral, where C is the curve who has this absolutely awful parameterization containing a product of exponential and trig functions in each component. Okay, so we get to assume that the vector field is conservative, and our first goal is to find the function f such that the vector field that we are given is the gradient of this potential function. So let's think about what that would imply. That would imply that 3 plus 2xy, the x output of the vector field, and x squared minus 3y squared, the y output of the vector field, are equal to f sub x, f sub y, respectively. Now let's break this down component by component. The first thing that this implies is that f sub x is equal to 3 plus 2x y. So in other words, someone took the derivative with respect to x of some expression, and the result of that was 3 plus 2x y. So I have to think the derivative with respect to x of what expression would give me 3 plus 2xy. So instead of taking a partial derivative, I'm going to take a partial integral on the right-hand side. I'm going to partial integrate (3 plus 2xy) on the right to undo the partial derivative that has been done on the left. So question mark, question mark, question mark is equal to the partial integral of 3 plus 2xy dx. But here's the crucial difference between this partial integral and the partial integrals that we did in chapter 12. The partial integrals that we did in chapter 12 were all definite integrals. We had limits of integration in our chapter 12 integrals. But this integral is an indefinite integral, the kind of integral where you would have a plus c on the end if you were in calculus 2. So let's think about that. If I integrated 3 with respect to x, I would get 3x. If I integrated 2x squared y with respect to x, I would get x squared y from power rule, dividing by 2, canceling the multiplied 2. But then I would also get some unknown constant, some plus c, corresponding to the indefinite integral. But it's more complicated than that. Remember that partially integrating with respect to x treats y as a constant, which means this plus c might not just be a number. Plus c might contain numbers, and it might contain y's, because the derivative with respect to x treats y as constants. The partial integral with respect to x needs to have a plus c, which acknowledges the fact that potentially there are some y's in here which disappeared when we took the partial derivative with respect to x. So I will call this the first c, c1, that could contain numbers and could contain y's as well. Now let's try it again with the second component. Let's deal with the ramifications of the statement that x squared minus 3y squared is equal to f sub y. So let's extract that, and we have step 2, f sub y is equal to x squared plus, I already forgot what it was, minus 3y squared. If I take a partial integral with respect to y to undo the partial derivative with respect to y, then I'll get x squared y from the first term. Integrating the second term with respect to y, I get y cubed, and then I get some unknown added arbitrary constant. But this time, because I'm integrating with respect to y, x is being treated as constant, so who knows, there might be a bunch of x's contained in this plus c term as well, f of xy. Alright, so let's compare what we got from these two calculations. We got on the one hand 3x plus x squared y plus some function containing y's and constants. On the other hand, we got x squared y minus y cubed plus some function containing x's and constants. Well, look at the overlap here. Here is a function containing x's and constants, which corresponds to this term containing x's and constants. And here is a term containing y's and constants, which corresponds to this term containing y's and constants. So if I match pink and orange, and if I fuse together these two equations representing the potential function f of xy, we can conclude that f of xy, the potential function, is equal to the mixed term x squared y minus the y term negative y cubed, and then the x term 3x is a potential function. For capital F. And you can go back and you can check that if you take the partial derivative with respect to x of this function, you'll indeed get this quantity 3 plus 2xy in the first slot. And you can indeed check that if you take x squared y minus y cubed plus 3x, take the partial derivative with respect to y, then you will get this second component here for our vector field. Okay, now that was just step one of this problem. We worked and worked, and we took partial integrals, and we found a potential function for the vector field that we were given. Now the process that we have just done, if you're planning to take differential equations, what we call here Math 238, you're going to use this process again of partially integrating in that class. So this is a valuable skill to have for that class as well, finding potential functions. For us, we are going to use the potential function in the following way. They said find the line integral of over C of vector field dot dr. Line integral over C of vector field dot dr, where r was the line integral parameterized by this expression. Now the work that we have just done to find the potential function will save us a bunch of work where we don't have to calculate the line integral with so much effort because of the fundamental theorem of line integrals, which says, hey, you worked so hard and you found the potential function of your vector field. You found little f here. Because of that, if you want to calculate the line integral of your vector field, just take your potential function, plug in the endpoints of your curve, and then take the difference. So let's see. Our curve here has the endpoints r of 0, which is equal to e to the 0 sine of 0, which is 1, e to the 0 cosine of 0, which is also which is 1. And then if I plug in the other endpoint r of pi, then I get the location. If I plug in t equals pi, the first component becomes 0. And if I plug in pi to cosine, I get negative 1. So I get negative e to the pi from plugging in t equals pi to this for this parameterization. So the fundamental theorem says that if you want to calculate this line integral, all that you have to do is plug in that output of 0, e to the pi minus sign to the function, which was the end point, the terminal point of our parameterization, and then subtract the initial point of your parameterization plugged into your potential function. Now both of these points have 0 for their x-coordinate, so that causes the first and the third term in the potential function to vanish. And I'm left with negative y cubed, so negative e to the pi cubed, minus negative 1 cubed, so minus negative 1 cubed, which can be simplified just a little bit to, I suppose, e to the 3 pi plus 1 is the value of the line integral. And that is the hardest thing, I think, about actually calculating line integrals for conservative vector fields, is just finding the potential function, and the rest is very easy. Okay, now we have one last theorem to go, which is a way of trying to discern if a vector field is conservative or not. If the vector field is conservative, then calculating line integrals becomes much easier. If the vector field is not conservative, then you know that you have a lot more work to do to calculate any line integral. So suppose that you have a vector field with component functions p in the x-coordinate, q in the y-coordinate. Now suppose you take the derivative of the first component with respect to y. And suppose you take the derivative of the second component with respect to x. If those two partial derivatives don't match up, then you know for sure f is definitely not conservative. Calculate these mixed partials, the derivative of the x with respect to y, the derivative of the y with respect to x, and if they don't match, f is definitely not conservative, and you're going to have to do a lot more work to calculate your line integrals. So as a very quick example, let's show that the vector field f of xy equals y squared. X is not a conservative vector field. So we have the function p of xy, the x component, which is y squared, showing up in the first component here. And we have the partial derivative of p with respect to the second variable is equal to 2y. Now we have the function q, which shows up in the second component of the vector field, that's x. If we calculate dq dx, we get 1 for the result. And these results are not equal. And because those results are not equal, this vector field is not conservative. So don't even waste your time trying to find a potential function. There is no potential function for this vector field. Now be warned, this theorem, as yet, the only method we have to show that a vector field is conservative is to find its potential function. The only way that we have to show that a vector field is conservative is to say, hey, I found this function lowercase f, and my function is the gradient of this lowercase f. This theorem that we have given above is another one of those one-way theorems. This theorem can be used to show that a vector field is not conservative, and in general, you cannot use the opposite to show that a vector field is conservative. If these two partials happen to match up, you still don't know for sure whether the vector field is conservative or not. If these two happen to match up, then who knows what's going on. The vector field may be conservative or it may not be conservative, but you need to find out some other way. It's another situation like we saw in Calculus 3, where we had the divergence test, which very easily showed that a series diverges, but if the divergence test was inconclusive, you had to go to some other test. So just be careful. That situation has come up once again.